Okay, so here we go. So let's just practice here. I've got a graph of a function, and we're going to focus specifically between x equals 1 and x equals 3. And so just in general, whenever you graph something, whether it be a line or a surface or a region, we're going to talk about regions today. If it's a line, if it's a curve, what is it that you're graphing? What is it that you're graphing? Solid in three dimensions, a curve in 2 dimensions, a surface. What are you graphing when you graph something like any one of those things? Yeah. Right. Yeah, whenever we graph something in the plane or even in 3D, you'll do a lot of that in Calc 3, you're graphing a set of points. It's really helpful to think about it that way in terms of what is the mathematical expression or equation that will generate that set of points, right? So you're saying, what's true mathematically that will give me that set of points? So if I want, say, if I want to express this set of points right here, okay? Now I've already said that x is going to be between 1 and 3. All right, this is my function f. So what's going to graph all of these points? What's true about all of those points? How am I going to graph those? Now I've already said that those points are going to be between 1 and 3. Here's 1 and 3. So what's left to specify that set of points right there? Yes, sir?
So it would be the set of points less than the function but greater than y equals 0.
He wants the set of points less than the value of the function, but greater than 0. So how would we write that all in one expression? So we can go from least to greatest, right? We use less than signs, go from least to greatest. What's the least? 0 is less than. What is it about these points that we want to be greater than 0 and less than the function? Y values, right? Y values less than the x values. Okay, and so that should give us a nice red region there. Okay, so I want you to think about, write down, what would you put, now I want to get the second region here below the x-axis. So in a new statement now, again, I've already specified that x is between 1 and 3. What am I going to write to get all these points down here? So again, we're thinking about an expression that defines mathematically what's true about all those points. If we get that mathematical statement correct, then graphing calculator will show us all those points, okay? So somebody new. How about in the light blue shirt here with the white stripes? Yeah. Did you get it? We want to get, I need an expression that's going to generate all these points right here. 0 less than y? Greater than y? Okay. Is that it? So I got that already. So are we done with the y values? Want all y values less than 0? Let's try it. So here's all y values less than 0 between 1 and 3. So, yeah, next. Okay, and so let's do it again. Let's do it from least to greatest to be consistent here. So from least to greatest, what would it be?
So f of x is less than 0, which means less than y, which is less than 0.
He wants this. So yeah, so all y values that are greater than f of x above the curve and less than 0 below the x-axis. Okay, so that's just a quick little review of that first section. So you know from your reading that this is all about, we want to think about adapting integrals to area, right? And it's going to be specifically area as defined by a function, a curve, such as this. So like, how can we write an integral to say find that the area of that red region or that blue region? Okay. So if we start thinking about integrals to compute area, then what is an integral? We know an integral is net accumulation, right? Net accumulation. So then what we're saying is that something like this, right? So this is consistent with what we talked about last week, that our net accumulation of area would be an integral of rate of change of area t dt, right? This is consistent with what we did last week. So if we're going to think about integrals as area, then we're going to think about accumulating area, right? That we want the net accumulation of some area, right? And what's the key thing that we need to do that? Rate of change, right? So if we're going to write areas as accumulation, or as, areas as integrals, then we need rate of change, right? But then the second question that it raises, so that raises two questions, and the first one we talked about, we said, what is the rate of change of area of the region we are tracking, right? If we're going to write it as integral, we got to have that rate of change function. Second question is, what does using integral for, quote, area give us, or give as the function carves out regions above and below the x-axis? So we've got to kind of investigate what's going to happen as the function changes from positive to negative, negative to positive. What is that going to mean if we're trying to write something to do with area in terms of an integral? So
You need negative and positive areas.
yeah, so this is the question we'll ask. So yeah, just posing that question.
Oh, sorry.
Yeah, but yeah, if you already know the answer to that, good. So, and you should have an idea based on the reading. Okay, good job. All right, so in terms of, let's see here. So we want to think now about rate of change. Where does this rate of change of area going to come from? Okay, so let's. Not working. So again, so rather than think of area as just here's the region, what's its area? If we're going to be using integrals, we want to think about accumulation of area, right? We want to think about accumulation of area and writing a function for any amount of area, right, as x increases. So we're really going to think about not blocks of area having single values, but an accumulation function that accumulates area, or something that has to do with area, okay? All right, so again, it goes back to rate of change, right? If we're going to set up an integral, we need rate of change. Okay, so to determine the rate of change of area, we're going to begin with the easiest example there is, which is constant rate of change, right? Constant rate of change. So what would a region increasing at a constant rate look like? So if you had a region, what would it look like if it was increasing at a constant rate? Increasing at a constant rate. When I plugged my computer into the display, GC shutdown. And all my all my last changes didn't get saved. All right, here we go. All right, so here is an example of a region whose rate is increasing at a constant rate. Would you agree? Okay. How about now? Watch this. Ready? Watch this. Is it increasing at a constant rate now? Did it increase at a constant rate that time? Yes or no? Okay, some are saying yes, some are saying no. So those who are saying no, someone, why do you say no? It's not increasing at a constant rate. I'll do it again. Ready? Increase it. What's that? Okay, he said with respect to time, it's not increasing at a constant rate. Would you agree with that? Yeah, as time went by, there was a little change and then it stopped. And then there was a little more change, and at the end it changed real fast, right? So if you're thinking no, then you're thinking in terms of time, which is correct. I never specified with respect to what variable. So yes, with respect to time, that's not increasing at a constant rate. But could this still be thought of as increasing at a constant rate? Even if it's doing this. We're talking about the area now, so we have the constant rate of area accumulated. With respect to what would be a constant rate? With respect to y? With respect to the width of the region, right? With respect to the width of the region. So if we call that, we're going to call that x, right? So because it's kind of like the x coordinate here, right? So the width of the region is going to be x, and we'll say that's in inches, say. Okay, doesn't matter. And so with respect to x, yes, that area increased at a constant rate. Okay, with respect to time, if I'm jagged with the way that if it increased a little bit and then a whole bunch and then it stops, then no, not with respect to time. But we're interested in with respect to x. Okay? So if we had a value of a constant rate, say m, of the constant rate of area with respect to x, what would it mean? Review from week 1. So what's the meaning of m, the constant rate of area with respect to x? I think you're going to need to pair up and refresh this one. Pair up and talk about a good full definition of what that value m would mean, the constant rate of change of area with respect to x. Go. Talk it out. All right. See if we retain this from Calc 1 or from last week at least. What's a good broad meaning of this value of m? Somebody new. What'd you talk about with your partner? Yes, sir.
So m is that for any given change in the width, or I don't know what we're calling x.
Yeah. Yeah, the width this way to the right is x.
Okay, any given change in the width, the area is equal to m times that change.
Almost. What's equal to?
The change in area.
Change in area. Okay, right? Right. So this is what you guys should have talked about. Given any change in x, the width of the rectangle change in area equals would be what? What's that? No. So we're not talking about any numbers yet. So we're just saying if we knew that constant rate of change m, given any change in x, what would the change in area be? Yeah. Right. It'd be that constant rate times the change in width. It's just right, exactly. In other words, what? dA equals m dx, right? This is our constant rate of change equation that frames the meaning for that constant rate given any change in x. Okay, so what we're going to do is we're going to use that and kind of work backwards a little bit to figure out what m is, right? So we're going to use that and we're going to make a table. So for instance here, we'll let x be 1. All right, so we're going to let x be 1, okay? Need to toggle. Time me. See how long this takes me. Okay, got it. Finally. Okay, so I'm gonna let x's go from 1 to 1.5. Okay? And you're gonna figure out as x goes from 1 to 1.5, what does the area do? The area goes from what to what? And then we're gonna write down what dx is and dA. And then as a result of all that, m. Okay? So as x goes from 1 to 1.5, what does the area go from? All right. So what is the area here? So can you see that? So what was the area when x was 1? 3. What's the area when x is 1.5? 4.5. dx is? The change in x is a change of x, so we're going to change the width by 0.5. We get a change in area of 1.5, which for that case would mean that m was? Right? Because of changes in area, or m times dx, that would mean that rate of change was 3. Okay, so I want you to do it for 5 to 5.2 and 4.6 to 4.7, say. That's good. We'll just do 3 examples there. So, how does the area change as x changes from 5 to 5.2? What's the resulting dx, dA, and then m? Compare all the numbers with the person next to you once you're ready. When you're ready, compare the numbers with the person next to you. Okay, any questions about building this table? Does it make sense what we're doing? So we're kind of, by knowing what the areas knowing what the areas are, we're kind of back calculating what the rate of change is, right? So what, in that second example, what is dx? 0.2. And what'd you get for dA when you found those two areas? What'd you get for dA? Did you get 0.6?
Yes.
The change in these areas, because this would go from what? 15 to 15.6. All right, so that indicates what rate of change? 3 again. One more time. Your change in area here was 13.8 to 14.1. Agree? Corresponding change in x? 0.1. Change in a? 0.3. Again. It's looking like the rate of change is 3. Okay? Now, this is not a proof, right? This is not a proof. We can't possibly try every single case, but you read a proof in the book, okay? There's a proof in the book of this same principle here, which I'll let you just refer back to. But what are the units on this? So this rate of change is 3. 3 what? What are the units? Rate of change of area here. Okay, lots of you are saying inches squared per inch. Inches squared per inch. Right? Because it's how much the area changes for any change in width in inches, right? How much the area changes for any change in width in inches. Okay? So when it comes to integrals, we want to integrate functions. So let's think about the top of that region then. Being a function, say f. Okay, so now what I'm doing is I'm saying let's make the top of that blue region a function f. Okay? And so what do you notice? So we said that this area is increasing at what rate? 3 inches squared per inch. What do you notice about the function f? What is f of x? F of x equals 3. Okay? So if we're taking from our area example, what would the units on f of x be? Just inches, right? It would just be whatever your y coordinate unit would be. It would just be inches. So notice, the units are different. We don't want to divide out an inch, inches squared in inches and get inch, right? Because we want this to truly reflect a rate of change of area with respect to a length. So we want to keep that inches squared per inch. But f of x is inches. But the key thing that we're going to use here is that the values are the same, okay? The values are the same. Noting that the units are different. This is a rate of change, and then this is inches, or really could be whatever unit f is in. Whatever your output variable, your function f is, that's the unit. So it could be, mass or temperature, something like that. But in terms of now, if we want to find that area, the value of that constant function 3 is the rate of change of that area being swept out. Okay, so we can note that the values are the same, but keeping in mind that the units are different. Make sense? Okay, well that's easy because that's a constant function, right? So what about a non-constant function? So same situation. What about a function that's not constant? How are we going to handle that, right? So again, it's kind of the same thing we looked at last week, right? We started with a constant, looking at constant rate of change, and then we said, well, what if the rate of change is changing? So how do we deal with that? So let's take a look at this right here. There's a nice animation. So here's this function as y equals f of x. Should watch this. So what just happened there is what just happened? Did you see what happened there? Right. So whoever made this video drew a box around the video around that spot, and then caused it to zoom in on that spot on that box. Okay. And what do you see here? Yeah. So that smooth curve is being approximated here by what? Little constant values, just like we did before, right? We took a changing rate of change function and we made it into a pretend function of constant rates. So we do the same thing here. We got a changing function, and we're going to reproduce it with little constant segments, right? Segments of constant value. And if we do it again here, so now make the box, zoom in again. So now this is looking a whole lot like our first example, right? So we're zoomed way in on the curve, but for a given small interval of x here, for say from point, what's this, about 0.94 or so to 0.96, we've got a constant rate. That's pretty close to the actual changing value of the curve, right? So we can think of that as a constant function, right? Constant function that's very close to the changing value of the function, okay? And what did we just found? So if we were to look at that and think about the area below that red line down to the x-axis, what did we find that the rate of change was? So what's the rate of change of that area increasing in this interval? What is that rate of change? About what? So what's the rate of change of area of x right there? Yeah, about 1.6 or what? So it's like about the value of the function, right? So like f of 0.94. So by changing a function who has changing values into a lot of little constant values, each one of those now, if you're thinking about area being swept out, each one of those then is like our first example, and the rate of change of area being swept out is just the value of the function there. Units are different, but the value is the same. So right now, the rate of change of area is about 1.6 or 1.61, 605, something like that. Right now, that's how that. And now in the next interval, the rate of change of area is 1.63, or f of 0.96. F of 0.96. Okay, so let's kind of summarize this here. So if we think about we're going to start at A. And say here's our value t, right? Here's our value t. That's increasing through small intervals from A to X. So now the book uses this notation. We used that last week to mean what? The approximate net accumulation function, okay? We mean that. But now the book is using that to mean area function, right? Area function. Or exact accumulation of area. So this was our question. What is R sub A of t? What is the rate of change? Right? So for any given value of t between A and X, so t is increasing through little intervals from A to X, what's the rate of change of area with respect to t? Yeah, so it's going to be that, what we saw. It's going to be like the big example we had where it was 3. Well, now it's just for that little tiny interval, it's going to be the value of the function, or what? So what is the value of function there? F of t, right, f of t. Okay, so that is a good start, but we've missed a really, really important aspect of this, right, which I meant to get to today. What aspect of this did we miss? Yeah, so we're really, with integrals, we're really not finding area. We're finding what's called signed area, and that's what I was going to get to next. That when f goes below the x-axis, now all those function values are negative. And what happens when you take the integral of when your function is negative? Your net accumulation goes down. Okay, so we'll pick that up one second.